Welcome to video lecture. Data structure, 1. Today we are going to discuss about data structure, need of data structure, algorithm, relationship between algorithm and data structure.
What is a data structure? What is an algorithm? If you look at standard definitions of these terms, it's easy to think that they're super complicated concepts. How do we really interpret these definitions? I like to think about data structures and algorithms using the following analogy. Let's say you've been buying a few books recently. Right now, you have a pretty simple organization scheme. As soon as you get a book, you stack it on top of the last book. This ingenious organization scheme has been patented by college students all over the world and has proved to be highly effective. Now, let's say you want to find a specific book from this stack. How would you do it? The most straightforward way to find a book is by taking a book off the stack until you find the book that you're looking for. I know what you're thinking. What does this have to do with data structures and algorithms? But believe it or not, you just saw a textbook example of a data structure and an algorithm. In this example, you can think of a data structure as our stack of books, and the algorithm we use to find a book is the process of taking books off the top of the stack until we find the book that we are looking for. But as time goes on and you start getting a lot of books, you decide to become a little bit more organized. You decide to buy a bookshelf and put all your books in alphabetical order by the authors. What do we do now if we want to find a book? You probably would start in the middle and slowly hone in to the appropriate place of the book based on the order of the alphabet. Here, the data structure would be the bookshelf organized alphabetically, and your algorithm would be your search process. Now, let's say as you get even more books, you decide to change your organization scheme one more time. You now basically have a small library, and each shelf is split based on fiction or non-fiction, and then the respective genre. Within each genre, you'll keep the same alphabetical organization of authors, and now, if you want to find a book, you can narrow your search to the corresponding section. Here, your data structure is this hierarchical organization of books based on genre, and your algorithm is the process by which you identified the genre and then found your book. So, taking a step away from this analogy, I think a really simple way to think about data structures and algorithms is the following. A data structure is a way to organize information, and an algorithm is a way to process information to reach an end goal. Some of the ways of organizing and using information are not at all obvious, but they all have their strengths and weaknesses, and a lot of this subject is about understanding these trade-offs. In the following videos, I'll introduce some fundamental data structures, talk about how you would go about designing them, and then talk about their performance. After we get through some key data structures, we'll get into some important algorithms that use these data structures to solve a variety of problems.
Next we are going to discuss about algorithm.
Now this will be a very basic introduction, so many of you have probably been exposed to a lot of these concepts already. This is primarily just for those people who have not seen anything in terms of algorithms or writing them. In this course, I will not be asking you to write really many algorithms at all. The only thing I ever ask is that you know how to trace through one so that you could determine the correct output for the algorithm. For that reason, this presentation will then define the word algorithm and all the common terms you might hear. I'll go over the main properties of an algorithm. I'll introduce pseudocode, and primarily today I'll talk about the if-then code, the while-do loop, and the for-next loop. And I'll also go about showing you how to trace through an algorithm. Now, I'm going to provide two different timestamps. You can either try this timestamp if you want to go to see the pseudocode section on if, then, while, or for next. I will also give you a timestamp here if you want to just jump right to the very, very end where I talk about tracing an algorithm. So just what is an algorithm? An algorithm just refers to a step-by-step process to perform some kind of action. That's incredibly wide open. That's a very, very open definition. So there's lots of things that we can call algorithms. The idea is credited to Ada Augusta, the Countess of Lovelace, who expanded on Charles Babbage's ideas of the analytical machine. Charles Babbage is the one who's basically understood to be or accepted to be the father of modern computing. But the idea of something that would compute something for you it's been around for a little while and wasn't really solely Charles Babbage's. But the idea of an algorithm or writing down the steps is sort of credited to Ada Augusta. Ironically, the word algorithm actually refers to a different man, actually from, I think it was 300 or 400 AD. So it's a really, really old idea, at least that idea. It's also the idea of algorithm, also corresponds from algebra, and there's lots of other things that are like that too, that are connected to that word. Now here's some common terms that we'll be using. A variable just refers to a specific location in the computer's memory, and it's used to store one and only one value. You have to tell the computer, though, what kind of data it's storing so it knows exactly how much space to allocate to that variable. That's why every variable has associated with it a data type. It tells the computer then basically, hey, when you go to this location, here's how you should interpret the data that you see. It's an integer, and it requires this much memory in order to store this particular integer. A statement, though, in a code for us will describe one step to follow in the algorithm. I'll refer to it many times as a line of code. Now, it's not a statement as far as a proposition. It is not true nor false. It's just called a statement of code or a line of code. Now, there's certain properties of algorithms that we have to agree upon in order to do much of anything. Every algorithm has an understood input. It uses values from a specific set. So then it says this algorithm is used on integers. For that input, there's an understood defined output. When I run this algorithm, this is the data value or output that I will generate for you. It produces certain values from a certain specified set. Now, the algorithms are also very precise and they're correct. The steps are very precisely defined. We know exactly what needs to be done and in what order. Also, it's understood that the input and output are connected to each other in such a way that if you give me an input, I get the correct output. I don't get some kind of goofy result. Also, the algorithm has a property of finiteness. It doesn't mean there's a finite number of steps. I mean, there really has to be because we're typing it, right? But it's done in a finite amount of time. I don't want an algorithm that never ever stops, or it takes longer than the life of the universe to complete. That would be a stupid algorithm, at least for us for now. Algorithms also are deterministic and apply in general to many types of input. They're deterministic. That means that every line of code, its value or output depends only upon the previous line of code and the current state of the machine. In this case, the current memory that's being stored for all the different data values. Generality means that in input, you tell me what the computer is supposed to accept. But generality means that you can make the input be anything from that set and it will still produce an output for you. Now, I'm about to go give you an example. To do that, I need to show you how to trace an algorithm. The thing is, though, there really isn't a standard way of how to write down a trace. To trace an algorithm just means that I provide you a step-by-step account of the algorithm for given some kind of input. There is no way to represent, there's no uniform way to represent a trace. So just please do your best to express what happens. When you do so, be organized. Usually make a table of some kind. Also, don't kill yourself. This is not that serious. Just make it be in such a way that I understand the state of the machine at the line of code you're working on and what the result would be. I'm going to show you kind of what I do. This is something I just made up, so it's not like someone else does it.
Next we are going to discuss about algorithm with an example.
What's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm does twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all, since there aren't any pairs of people in the room, and so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2, but then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s, but beyond that it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to solve problems. These were just 3. What problem would you solve with an algorithm?
Next we are going to discuss about relationship between algorithm and data structure. Well,
Algorithms is about solving problems efficiently. A bad programmer ranks in algorithms efficiency. Say we wrote a function that goes through every number in a list and adds it to a total sum variable. If we consider adding to be one operation, then running this function on a list with 10 numbers costs 10 operations. Running it on a list with 20 numbers costs 20 operations. Say we wrote another function that just returns the first number in a list. Then no matter how large the list is, this function will never cost more than one operation. Clearly, these two algorithms have a different time complexity, or relationship between growth of input size and growth of operations. We communicate these time complexities using big O notation. Referring to input size as n, common complexities are constant, linear, quadratic, logarithmic, n log n, exponential, and factorial. Our first algorithm runs in O of n, meaning its operations grow in a linear relationship with the input size, which in this case is the amount of numbers in the list. Our second algorithm is not dependent on the input size at all, so it runs in constant time. Let's take a look at how many operations a program will have to execute in a function with an input size of 5 versus 50. It might not matter when the input is small, but this gap gets very dramatic as the input size increases. If n were 10,000, a function that runs in log of n would only take 14 operations, while a function that runs in n factorial, for big O notation, we drop constants, so O of 10 times n and O of n over 10 are both equivalent to O of n because the graph is still linear. And big O notation is also used for space complexity, which works the same way for how much space an algorithm uses as n grows. Unless you sit in your room doing algorithms all day, there's a good chance you forgot what logarithms are. Logarithms are the inverse to exponential functions. In computer science, this is the binary search. But for the binary search to work, the collection has to be sorted, which opens up a huge field of computer science, sorting algorithms. A very basic sort is a selection sort. You have one pointer at the start of the list and another pointer that is linear scan to find the next minimum element. Then you swap those elements and increment the pointer. Since you're doing a linear scan for every element in the collection, this runs in O of n squared. A more efficient algorithm is a merge sort. A merge sort splits a collection in half into sub-collections until those sub-collections can be sorted in constant time. And then it works its way back up by merging sorted sub-collections until the entire collection is sorted. Since it's splitting in half, there will be log n splits and thereby log n merges. It is O of n to merge two sorted collections into one sorted collection. Since we're doing that log n times, the time complexity is
Data structures. Need of data structures. Algorithms. Relationship between data structures and algorithm. Thank you.